Good morning to all of you students. We are doing our 7th unit of chemistry, that is the equilibrium. And in our last lecture we have studied the relationship between the equilibrium constant in terms of molar concentration and partial pressure. And our today's topic of discussion is the applications of equilibrium constant. Before considering the applications of equilibrium constant, let us summarize the important features of equilibrium constant as follows. Characteristics of equilibrium constant. Expression for equilibrium constant is applicable only when concentrations of the reactants and products have attained constant values. Clear? Means when concentration of reactants and products is in equilibrium, both sides we are having a constant values. Clear? The value of equilibrium constant is independent of initial concentrations of reactants and products. Clear? We have to take the product of molar concentrations, not of their initial concentrations. So we can say that equilibrium constant value is independent of initial concentration of reactant A and reactant B and product C and product D, because we have to write the expression like that. For equilibrium constant, concentration product of concentration of C to the D, the A and to the B raised to its stoichiometric coefficients if we are having some. Clear? Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. Means equilibria can be shift forward or backward while increasing or decreasing the temperature limits. And the next characteristic, the equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. For example, I am having value of equilibrium constant for forward reaction, that is when reactant A and B are reacting to convert to the product C and D. Then value of equilibrium constant I will use Kc. And if I have to reverse the reaction, then the value of equilibrium constant will be K dash C. That is for first reaction, equilibrium constant is Kc. For second time, when reaction will be backward, equilibrium constant is K dash C. Then if I have to relate both these equilibrium constants, then value of K dash C is equals to the inverse of Kc. Clear? And the next is the equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Clear? Now we will see the applications of equilibrium constant, where we can find out the actual use of equilibrium constant. For any chemical reaction, we can predict the extent of reaction on the basis of its equilibrium, on the basis of its magnitude. Clear? And second application, predict the direction of the reaction. And third, calculate the equilibrium concentrations. These are the applications of equilibrium constant. So let's start with the first, that how we can predict the extent of a reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction, but it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. So the magnitude of Kc or Kp is directly proportional to the concentration of the products. How we can write? We always write that Kc is equals to the product of the products C and D and to the reactants, product of the reactants. Like this I will write it always. Clear? So this implies that a high value of K is suggestive of a high concentration of products and vice versa. Means when I can expect from this expression the value of K is higher. When we are going to have higher value in the numerator means concentration of products should be high as compared to the reactants which are given in the denominator. Definitely then we are going to have higher value of the equilibrium constant. So we can make the following generalization concerning the composition of equilibrium mixtures. So first, if value of Kc means equilibrium constant given in terms of its molar concentration having a value greater than 10 raised to power 3, product predominate over the reactants, means the concentration of products will going to be very high as compared to the reactants. If Kc is very large, the reaction proceeds nearly to completion, means maximum amount of reactants is converted into the products. Consider the following example. In this example, we can say that maximum amount of hydrogen and oxygen is converted into the products. The reaction of hydrogen with oxygen at 500 Kelvin has a very large equilibrium constant Kc having value 2.4 into 10 raised to power 47. Clear? What does it indicate? That maximum amount of reactants will going to be converted into the products. And second example, we can have reaction between hydrogen and chlorine. It will going to be converted into hydrogen chloride at 300 Kelvin has value of Kc equals to 4 into 10 raised to power 31. And then third, reaction between hydrogen and bromine, which reacts to give hydrogen bromide at 300 Kelvin. Value of equilibrium constant is again very high, 5.4 into 10 raised to power 18. Means maximum amount of reactants is converted into the products. And the second case, if we are having the value of equilibrium constant that is given in terms of molar concentration is less than 10 raised to power minus 3, the reactants predominates over the products, means the concentration of reactants will be high as compared to the products, means in denominator side we will going to have a higher value. If Kc is very small, the reaction proceeds rarely. Consider the following examples. Means we can say reactants will not going to be converted into the products. Definitely the proceeding rate of reaction will be very slow in that case. Clear? So we can study this with the help of the example. The decomposition of water into hydrogen and oxygen at 500 Kelvin has a very small equilibrium constant. Value of equilibrium constant is 4.1 into 10 raised to power minus 48. And second example, reaction between nitrogen and oxygen, which will be converted into nitric oxide at 298 Kelvin and has value of equilibrium constant, that is 4.8 into 10 raised to power minus 31. Clear? As the values of equilibrium constant in terms of molar concentration shows, it will going to have a very small values. So definitely the reaction will going to proceed in forward reaction with great difficulties, or very small amount of reactants will going to give products in these case. And if Kc is in the range of 10 raised to power minus 3 to 10 raised to power 3, appreciable concentrations of both reactants and products are present. Clear? If we are saying here, if we are having the value of equilibrium constant in terms of molar concentration in between the range of 10 raised to power minus 3 to 10 raised to power 3, we will going to have a appreciable concentrations of reactants and products. Consider the following example. For reaction of hydrogen with iodine to give hydrogen iodide, we are having value of Kc equals to 57 at 700 Kelvin. And also gas phase decomposition of dinitrogen tetraoxide, that is N2O4, to nitrogen dioxide is another reaction with the value of Kc equals to 4.64 into 10 raised to power minus 3 at 25 degree Celsius, which is neither too small or nor too large. Hence, equilibrium mixture contain appreciable concentrations of both dinitrogen tetraoxide and nitrogen dioxide. These generalizations are illustrated in figure given below. This figure shows dependence of extent of reaction on equilibrium constant Kc. If we are having its value greater than 10 raised to power 3, then we will going to say reaction proceeds almost to completion. Means in this direction, if we are going to see it in detail, on the left hand side, reaction hardly proceeds. Means at this point, value of Kc will be lower than 10 raised to power minus 3. Means in these area, I can say K is less than 10 raised to power minus 3 and concentration of products is negligible on this side. Here reaction hardly proceeds, means reactants are not converting into the products at a very higher rates, and at Kc both reactants and products are present in equilibrium at this position when we are having the value of K equals to 1. Clear? And after that, again, when the value of Kc, as we are moving from left to right hand side, is greater than 10 raised to power 3, means the concentration of products will be maximum concentration of products. Here I have written it as a product. Clear? And then we can say that large amount of reactants is consumed to give products. Clear? So how we can predict the extent of reaction? If value of equilibrium constant is less than 10 raised to power minus 3, then we can say that reaction proceeds very hardly, as the concentration of products is very small as compared to the concentration of reactants. At equilibrium, when the value of equilibrium constant is lying between 10 raised to power minus 3 to 10 raised to power 3, then we can say both reactants and products are present at equilibrium. And when value of Kc is greater than 10 raised to power minus 3, reaction proceeds almost to completion, means concentrations of products is very high as compared to the concentration of the reactants. So this is the first application in which we have studied how we can find out the extent of a reaction. Clear?